we can start another chapter. This is called Design for Additive Manufacturing. So this is another chapter discussing the whole additive manufacturing process in a broad manner, and we will be discussing some critical issues for designing some specific parts to be fabricated on additive manufacturing machinery. And we use the term abbreviation DFAM for most of the time. So it briefly means that you should be aware of the rules of additive manufacturing technologies, machines, and then design your products accordingly. And why are we designing for additive manufacturing? Since we want to take advantages of additive manufacturing technologies. If you follow the same design rules you are using in the conventional manufacturing operations, you will not be actually taking the advantage of additive manufacturing, and you may be wasting your time, wasting your money. So that's why designing is highly important, and you should always try to make some designs which are highly suitable for additive manufacturing. So let's briefly discuss first design for manufacturers. This is the term we use before additive manufacturing. We have conventional manufacturing technologies, conventional, let's say, tools, and we always have some actual rules in our mind and try to design accordingly so that the manufacturing will take actually less time, it will cost less, and in a shorter time you'll obtain the desired product. But this time in additive manufacturing the rules are modified, so that's why we need to also change the design paradigm right now we have. This is actually quite difficult since for, let's say, more than 100 years, we're accustomed to the rules for the conventional manufacturing. So in summary, if you are following design for manufacturing approach, then you should be tailoring your designs according to the needs, according to the properties of conventional manufacturing and assembly operations. But now we need to modify these rules so that we will be taking the advantages of additive manufacturing technologies. And that's why we call it as design for additive manufacturing. And many companies these days are following this paradigm and trying to obtain such products which are designed according to the rules of additive manufacturing. And you see many aerospace companies, other manufacturers. For instance, if you simply consider the hearing aids we just discussed in a moment ago, they are using the principles of additive manufacturing. They do a kind of a scan, they got the results, got the digital data from the customers, and then fabricate their hearing aids according to their size of their, let's say, ears. And that's quite a nice way of additive manufacturing, since we are taking the advantage of using the advantages of additive manufacturing. So why do we need to have such an approach? Since in additive manufacturing, we can have customized products, we can have easily produce very low number of products and some high numbers of products. Not mass production, but up to maybe medium-sized production. And the advantages, as you know, customized production. And we can easily do some changes on these customized products. It has many advantages. You can decrease the amount of assembly time, since in additive manufacturing, as you know, we can produce functional parts in the bath or in our different technologies. You don't need to do further assembly. With the help of them, you can decrease the overall manufacturing costs, and this will save you a lot of time, money, and other things. And by using additive manufacturing, we have actually some main properties. In additive manufacturing, we can have complicated shapes, we can have hierarchical complexity, which means that you may have multi-scale structures. For instance, in this part, you may have micro parts, micro materials here, but metal scale parts in the upper part of your overall part. So it's quite possible. You may have material complexities, composite materials, or some transitions in between materials is possible with additive manufacturing. And lastly, we can have functional parts. And that's why we are trying to design our parts according to additive manufacturing, since we want to make use of these properties in additive manufacturing. And in design for manufacturing, we need to, if you want to take advantage of manufacturing or design your products according to the principles of manufacturing, then you need to know all the manufacturing technologies, assembly steps, the capabilities of your supplier, whether they are going to bring the materials in time or not. You need to be aware of the behaviors of material. For instance, aluminum might be a good choice for your application, or steel. So you need to be aware of the properties of such materials. It's quite simpler, but the thing is that we have many possibilities in terms of material manufacturing. So that's why it's quite difficult and time consuming while you are especially designing complicated parts. And in the design for manufacturing efforts, you need to also be aware of some standards. You need to be a part of a team. You need to talk with all your engineering colleagues, and have, with the help of these discussions, you need to come up with a proper design. There are some handbooks for that, but again, it's not alone enough for that. You need to have engineering intuition. You need to be using some specific engineering tools, analysis software. With the help of all these knowledge, we can design finally for manufacturing. But in design for additive manufacturing, things are not that complicated. By knowing few rules, few additive manufacturing technologies, you can design some parts which are taking the advantage of additive manufacturing machines where you have in your company. So now let's discuss this issue, this comparison between design for manufacturing and design for additive manufacturing. This camera spool, as you see, it's a bit complicated shape. We have some ribs and some pockets. As you see, it's quite difficult to do it on a CNC machine, right? Can we do it? What do you think? Is it possible to do it on a turning machine or a milling machine, CNC milling machine? Can we have it on, let's say, 5-axis machine?
We would need to combine both methods.
Yes, with a single manufacturing is quite impossible. You need to have at least 2 stations. Some of manufacturing steps might be complete on the first station, and then the rest can be done in the second station. But what about, yes, mill turn might be, but you need to spend lots of time on mill turn machines. But it's possible, especially if you have some tools on the tailstock, since you need to also have a hole at the side. But for the other parts, it's quite possible to use mill turning machines. But now we will be discussing injection molding. So what do you think? Is this part can be injection molded or not? With a single part, with a single mold, is it possible?
Yes.
Single mold. Is it possible to have such an part produced with injection molding?
It's got to be at least 2 parts mold.
Yes, we cannot do it with a single mold since we have many pockets, some holes. We need to use, and this is circular, by the way. We cannot easily take it out from a single mold. At least we need to have 2 molds, 2 mold parts, and we need to have some cores. And cores will be embedded into these pockets so that after the casting is over, you can easily take your part out of the mold. And this is possible, but you need to spend more time. The cost is quite higher, especially if you are producing, let's say, tens of this product. But if you consider additive manufacturing, these are not problem for any additive manufacturing technology. For instance, you may use selective laser sintering if this part is made of polymer, let's say polyamide. You can use selective laser sintering and produce tens of this product in a single batch. And But if you want to do it with injection molding, then you may at least do 3 manufacturing sequences. Since in a single mold, I think in maximum you can have 4 number of products. But with additive manufacturing, you can have more than, let's say, 10, maybe even 50 products can be produced in a single batch, depending obviously on the size of your spool. Another comparison, this time we are comparing the number of parts. If you follow the conventional manufacturing and assembly approaches, for instance, if you look at this design, it has 16 parts. 1, 2, 3, 4, we have little bolts, nuts, so in some we have 16 parts. But if you do a consolidation, you can have a single part, and this is easily produced on an additive manufacturing machine, which means that you are decreasing the assembly time. In the additive manufacturing side, we have no assembly time, and so which means that you can decrease the time you are spending for assembly, and you don't need to have labor for assembling such parts. But what is the disadvantage of such a design in additive manufacturing? What is the advantage, or what is the advantage of having such a design composed of 16 different parts?
Easy repairing. Yani bir yeri kırıldığında vesaire daha kolay tamir edebilmek.
Yes, this is one of the advantages of designing with conventional manufacturing, designing for service. For instance, assume that this yellow part, not perfect yellow, but assume that this is yellow. In additive manufacturing, if this part is broken, then you need to replace the whole part. You cannot use it anymore. But if that's the case in the conventional manufacturing approach, you can simply take it out and replace with a new one. So this is an advantage of conventional, let's say, manufacturing and assembly approach. But on the other side, in additive manufacturing, we have consolidated all the parts. We have a single product, and in a shorter time with less labor, you can obtain the same part which has the same functions. Any questions, guys, on this example? Yes, we have shorter time. There's a question about the time. Since if you want to produce this one, you need to spend time on the lower part, time on the intermediate part. You need to use different manufacturing processes. For instance, you may be using injection molding for here. You may be using bending for this yellow part. And that's why it will take more time in terms of manufacturing. Also, you need to have time for assembly of these parts. But in the additive manufacturing side, you can do it in just a single manufacturing process. And again, you're not spending time to join the parts since we only have a single part. There's another question from Hussein. So if you want to improve the performance of this one, you need to spend more time. Obviously, there might be better solutions, but right now, this might be made of steel, for instance. This might be made of plastics. If that's the case, then additive manufacturing might not be a good idea, since they are made of different materials. But on additive manufacturing machinery, you can only produce, in most of them, you can only produce a kind of a material. Right now, we don't have a machine which is capable of printing polymer and metal at the same time. Since the temperatures are highly different with metals and with polymers, it's not possible. But if you're not actually, the material, if not is important for you, then additive manufacturing might be advantageous. But again, in additive manufacturing, you may not have a fully consolidated design. Instead of having 16 parts, you may have maybe 3 or 4 parts. Again, that might be a kind of a design for service. For instance, if this is the part which is breaking commonly, then you may do it separately in your additive manufacturing approach. So what is the main objective in design for additive manufacturing? We are trying to maximize the performance by actually doing some synthesis in terms of the shape of your part, the size, the hierarchical structures. You may have some lattice structures in some part or macro structures in other part of your design. You may have material compositions in some part. The density might be lower, but in critical parts, you may increase the density. And if you have such a synthesis of these properties, then that means, yes, you are on the good path. You are designing the part according to additive manufacturing technologies. So what are the main guidelines? We don't have a proper actually path, proper guideline, but we can briefly talk about some of them here. It's better you use kind of complex geometries if they are satisfying, if they are giving you better results. But if there is no change in terms of the performance, obviously it's better you not use complex designs. Another advantage, as you know, you can have always customized designs, customized geometries. If the parts are especially for people, then you can make use of this property. But if it's an part of a machine, then obviously you don't need to do any customization. You can just focus on the performance of your parts. And another thing, if it's possible, you should always try to join the parts, consolidate the parts so that you will not spend time on assembly of these parts. And by actually doing this, you should always be aware of the problems in the additive manufacturing technologies. You should be careful about the slicing planes, for instance, since if you remember, we said that in additive manufacturing, we don't have isotropic properties. We have anisotropic properties, and you should be aware of this issue and design your parts and orient your parts in the machine accordingly. Otherwise, you may have less performance after you manufacture your parts with additive manufacturing machines. Any questions, guys, about these fundamentals of design for additive manufacturing? Now I will be going into discussions of specific additive manufacturing technologies. So let's have a look at them. For instance, I will start with the layer thickness. And here you see we have different technologies: FFF, SLA, SLS, jetting, binder and material jetting, and selective laser melting. And as you see in all of them, we have different layer thicknesses. These are common layer thicknesses. If you remember, in FFF, we can decrease to 50 micrometers, but in SLA, this is a very low number, 25 micrometers. And we have the lowest layer thickness in material jetting. And we have high numbers for SLS and maybe binder jetting. So you should be aware of this issue and select your design, select your additive manufacturing technology accordingly, since they will directly be affecting the surface qualities. You will have, since staircase effect, even it's an, let's say, vertical surface, you will have such bumps on the vertical surfaces. Let's have a look at some rules, some main rules. For instance, we have two cases. This is our building table. And it says that obviously it's better we have such a chamfer instead of a fillet. So what do you think? This one is the right, the one on the right is better.
Hocam soldaki kalkma yapabilir belki tabladan uzun vadede.
Yeah, it's another possibility. But what about the slopes here, especially in this region? So if you consider this part, we have very low angles, right? Shallow angles, and you may need to have support structure. But if you look at here, the angle is always the same. It's around 45. So without using support, you can have proper planes. And if you look at here, this part will be obviously smoother, but the problem is that this region, this below region, will have less surface quality. And this is valid for any kind of additive manufacturing process. So in general, it's better you have such designs at the regions where you are actually touching the build plate or other regions. Now let's discuss these processes one by one. The first one is FDM or triple F. If you remember, in this process, we need to use support structures for overhanging regions. And that's why the orientation is quite important. While designing, you need to be aware of this problem and have some. Do you remember the dancing snowman? And they had a special part inside of the snowman so that without any support structure, they had a functional design. And why don't we actually want to have support structure, since it's waste of material, and it, again, decrease the surface quality, it increases your manufacturing time and post-processing time. So that's why we're always trying to have some designs where you have no support structure or less support structure. And you can do it by modifying your design or orienting your design on the tables. Another thing is the infill percentage. If the strength is not important for you always, it's better you have less infill percentages. This will decrease the overall weight and decrease the material consumption. Another issue is the shrinkage. Usually we have 1 to 3% of shrinkage in additive in fused deposition modeling. You should be aware of this issue, especially for fitting problems. If you have an assembly and if you don't consider the shrinkage, then probably the resulting part will not fit into your hole exactly. That should be considered while designing your parts. And you should be aware of the properties of the materials you are using. The PLA, for instance, has less strength compared to ABS, and their temperatures, for instance, PLA has a low glass transition temperature, which means that at around, let's say, 50 degrees, you cannot maintain it cannot maintain its shape. It will be deformed after 50 degrees, but if you are using ABS and its glass transition temperature is a bit higher, it can, let's say, maintain the shape around 50 degrees. So you need to be aware of all these properties. Another thing, bridging might be a nice idea. If you remember the letter H, if this length is not too much, then without having support structure, you may pass this part in a, let's say, faster manner, and you may turn your fans fully in this region so that it will be solidified, it will be cooled quickly, and you don't need to have support structure. So that might be used in some designs, but the thing is that you need to keep this actually distance as low as possible. Another important thing, the nozzle diameter, it affects directly the size of your minimum feature. Since, for instance, if you are using 0.4 millimeter of nozzle, then that means assume that you want to have a perfect circle, and we know that it's not possible since you have a kind of a circular nozzle. This will be moving, and while it passes through this corner, we will have a kind of an fillet at this corner, and this is the radius is 0.4, at least it will be equal to 0.2, and that's an important issue in FDM, and you should be careful about it. If you are producing very small parts having small features, then maybe you can switch to a nozzle size of 250 micrometers. Another thing, it's not possible to have layer thicknesses less than 40 micrometers, even 50 micrometers. So you should design your parts or have some requirements on the surface qualities depending on this minimum layer thickness. There's a question on chat. There are some software actually adjusting the orientation to have less number of support, less amount of support structures, but usually you need to do it manually, since it takes lots of time for CAM software to do this optimization. And actually we are more expert in terms of orientation, so I suggest you do it yourself and try to decrease the support structure in a proper orientation.